Hi, so let's continue on our final subtopic for chapter 8, which is angular momentum. Okay, so I hope that you all remember inside chapter 3, you've learned that momentum P is equals to mv, right? mv. So it's actually analogous to our angular momentum because we now want to study momentum in rotational motion. So again, the angular momentum is denoted by the symbol L, whereas I is the moment of inertia, which is denoted by M, analogous, and omega, which is the angular velocity, is analogous to V. Okay, so what is angular momentum? It is defined as the product, okay, as the product of the body's moment of inertia I and its angular velocity omega. So here is the formula lah, right? And here's where the L is the angular momentum, okay, I is in the moment of inertia, and omega is the angular velocity. The units of angular momentum is kilogram meter square per second, and it is in a vector quantity, meaning that has both magnitude and direction. Okay, so I hope you all remember inside chapter 3 the direction of the momentum is the same direction as the velocity. Okay, this is also true for the angular momentum. So the direction of the angular momentum here will be the same direction for the angular velocity. So let's see this diagram here. Okay, so you have here a wheel which is rotating here. So by using our right hand rule, we can grip our fingers to the direction of the wheel, and the thumb would point in the direction of the angular velocity. But since we know that the direction of the angular momentum would follow the direction of the angular velocity, so it would be the same. Okay, so angular velocity and angular momentum vector points along the rotational axis determined by the right hand rule. Okay, so I'm sure you remember conservation of momentum, right? So now let's explore conservation of angular momentum. Okay, but before we go into more detail for conservation of angular momentum, let's see here a bit of introduction for the conservation of angular momentum. So let's first assume, let's first assume the angular momentum of a particle. Okay, for a particle P of mass m. Okay, let's say you have many particles here, but let's say we take this particle here, okay, travels in a circle of radius r, okay, radius r, and has a tangential velocity v, as shown in this figure okay. So the angular momentum, this is another formula for angular momentum. You can find the angular momentum, it's a cross product between the distance of the particle to the axis and the cross it with the momentum, linear momentum lah, mv. Okay, so the magnitude of the angular momentum is rp sine theta, where theta is the angle between r and p. So you can see here, since p equals to mv, you can see that it's 90 degrees here, 90 degrees. Okay, so if you have sine 90, means that this is value of 1, right? So you have, and we know that P equals to mv again. This is my third time stating it. So you know that L equals to mrv, and we know this, our velocity is the distance between the particle to the rotational axis times the angular velocity. So substituting here inside our equation here, we should get L equals to mr square omega. Okay, one thing you need to know, okay, so why is this different from our L equals to I omega? Actually, it's not different. Okay, the general formula for moment of inertia I is actually mr square. So actually, okay, however that depends on the object of the body lah. Okay, so actually this would get you this equation. Okay, so you don't need to worry about that. Okay, so now let's go further to the conservation of angular momentum. So again, what is the principle of conservation of angular momentum? It's here, it states that the total angular momentum of a system, okay, remains constant, means that the system is isolated, so no external torque or external force acting on the system. So we can write this as L total, okay, equals constant, or, okay, this is very important, okay, the initial angular momentum equals to the final angular momentum, okay, and because the magnitude of the system is L equals to I omega, okay, we can express this as I initial omega initial equals to I final omega final. So I'm sure you remember this as M initial, okay, V initial equals to M final V final. Okay, so the conservation of angular momentum requires the product of I and omega must remain constant. So what does it mean? So we know that L equals to mv, right? Okay, so to follow the conservation of angular momentum, okay, the L must remain constant. Okay, L must remain constant. Okay, constant. So if the mass, for example, the mass were to sorry, so it's not L equals to mv. Okay, sorry, that's my fault. It's L equals to I omega. Okay, sorry about that. So if you want to have L remain constant, if the value of the moment of inertia were to decrease, okay, the angular velocity must increase so that the L remains constant. It cannot be both the I and the omega decrease or the I and omega increase. It must be when one of the symbol decreases, the other would increase. Okay, it cannot be both of them decreasing or increasing at the same time, because we want the L to remain constant in our isolated system. Okay, so let's try to view, okay, a few examples to demonstrate this. So we have two examples here, a ballerina here, okay, which, okay, has her arms upwards and her arms inward inside the second situation. So here is the initial angular momentum, and here is the initial, okay, here is the final angular momentum. So what can you see here is that first, when she draws her hands upwards, okay, the distance here, the distance between her hands towards the axis of rotation R is increased, and we've learned this inside the previous video. Okay, I equals to mr square, okay, summation usually, okay, summation mr square. So if you have increase in the value of R, means that your moment of inertia would increase. And what did I say from the previous slide? Okay, if you have I which increase, okay, to have the value of angular velocity, angular momentum constant, your omega must decrease, which is what this statement, the bottom statement here lah. Okay, arm stretch I, okay, is large, so omega is small. Coincidentally, if you see this diagram, okay, now her arms is moving inward, so the value of R here, okay, is very small, meaning that the I, okay, is also very small. What does this mean for the omega? If I is small, omega should increase so that the value of L remains constant. Okay, so when she pulls her arm, the moment of inertia is small. Again, when the moment of inertia is small, it means that the object is easier to rotate. Okay, in this case, the person is easier to rotate, so she would spin faster. Okay, so for our next example, let's see here. Okay, you have here, okay, a student here. I'm not sure why she's alone here. She's moving towards the center of the rotating platform. Okay, when she moves towards the center, the value of R would decrease. Again, when the value of R would decrease, means that the moment of inertia would decrease, means that the, okay, here the moment of inertia would decrease, the angular velocity of the system would increase, because now we want the value of L to always remain constant. See, constant. Okay, so for it to remain constant, again, when one of the part decreases, the other must increase. So in this case, when the moment of inertia, okay, when the moment of inertia decreases, the angular velocity must increase so that the angular momentum remains constant. Okay, so for our final example inside this chapter, you have here the swimmer. Okay, now she's pulling her hands inwards. When she's pulling her hands inwards, the moment of inertia is reduced, the omega is increased, means that it has more rotation. But then when she pulls her hands outwards, okay, now the moment of inertia increases. Okay, okay, you see here, there is something wrong. Okay, you cannot have moment of inertia and also the angular velocity increases. So this should be what? Decreases. So that's why she spins slowly at the end, so that she has less water splash. Alright, so okay, so that's all for our chapter 8. I hope that you enjoy this chapter. If you have any question, you can ask me, Sir Amin, or Sir Sulaiman, or Sir Aziz in the cubicle. Thank you, and I hope to see you again.